Okay, now is our second topic is about modeling the interaction among variables. So in a typical regression model, we have an dependent variable and a few independent variables. For each independent variable, there is a coefficient, and that measures how xi affects y. Okay, we are pretty familiar with that. But sometimes the impact of one independent variable on the dependent variable, sometimes the impact depends on the value of another variable. Okay, that's possible. For example, if we talk about the house prices, sizes, and the numbers of bedrooms may have some impact on price, but the impact may be different when size is different. If we have a big house with no bedrooms, then it's bad. In that case, the number of bedrooms may have a positive impact. But when our house is very small, then if the number of bedrooms is a lot, then that's bad. Okay? So when we have a small house, maybe one bedroom is better than second bedroom, and then two bedrooms and three bedrooms. But if our house is big, then one bedroom is it's worse than two bedrooms, it's worse than three bedrooms. So that's possible. Or if we consider a demand of a product, demand can be sensitive to price, right? And in typical cases, when price goes up, demand goes down. Or even if it's the other way, we still have price sensitivity. But the sensitivity may actually be different between different kinds of people. For example, between men and women, because this may be some special product that only men or women like it, but the other group does not. Or it may be different between students and the professors. It may be different between workers and employers. So that's possible. That's possible. In this case, we say there is an interaction between the two independent variables, okay? Because the impact of one variable depends on the value of the other variables, okay? So if we want to model the interaction between xi and xj, one possibility is to create a new variable, xi, xj, and that's the product of these two variables. And then we will put it into our regression model. We will get one coefficient, let's call it beta 1, 2. Beta 1, 2 measures the interaction between the two variables. The impact of x1 now becomes beta 1 plus beta 1, 2 times x2. Why is that? We still have beta 1 here. That's some impact when x1 goes up by 1. And also we have some impact here. When x1 goes up by 1, the impact is beta 1, 2 times x2. So you can also say that we are taking the first order derivative. But anyway, from the functional form, it should be clear enough. When x1 goes up by 1, the impact is beta 1 plus beta 1, 2 times x2. And that means the impact of x1 depends on the value of x2. For x2 is the same thing. The impact of x2 depends on the value of x1. In fact, in the previous lecture, we introduced a quadratic term, a quadratic transformation in a regression model, right? That's actually a special case of interaction, because then we are measuring the impact of x1, but the impact of x1 now depends on the value of x1, like some kind of curve we used in the previous lecture. When we have something like this, the impact of x1 depends on the current value of x1. Okay, the same thing here. The impact of x1 depends on some other variables, and it's not constant throughout the whole space. Okay, so that's how we model interaction. The answer is very simple. If you have two variables and you suspect that the impact of one variable on the dependent variable depends on the other variable, then you add a product term to the model. So in our example, we are asking the following. We are suspecting that people may have different price sensitivity for shows played at different time. So we want to ask whether time and average price affect each other's impact. Okay, if that's the case, then we want to add time and the average, we want to add their product. But time has been split into two variables, right? So that means we need to add the two product terms together into our regression model, like this. So previously we have 5 variables, now we have 7 variables, and these two variables are added into our model because we want to capture interaction. Okay, so we have some variables who are not directly related to time and average. We can see that capacity and year, they are still quite significant, so the impact is still there. And then for time and the average price related variables, we find out that average price now become insignificant. So average price itself is not significant. But if we take the interaction into consideration, there's a star here. That means the interaction between time M, between a morning show and the average price is significant. Okay, this is different from that. The time sensitivity for a morning show is different from the price sensitivity of afternoon show. So that's the information content here, and that's useful. That's useful. So if eventually we want to keep this variable, we must also keep all other variables here. Because if you want time M here, you also need time E here. That's something we mentioned in the previous lecture. And also, if you want these two variables, if you want average price in the interaction term, you need the interaction. You need the original variable. For time E, the same thing. So if you want this one, you need all the 5. And that's the typical thing we do. We find out whether there is something significant in the interaction term. If that's true, then we include all we need. So let's make some interpretations. One thing we find out is that time has an impact on the price's impact. So what does that mean? People have different price sensitivity for shows at different time. In particular, when the price goes up by 1, what's going to happen? If this is an afternoon show, then in that case, time E and time M, they will just be 0, right? So these two variables will not be here. And the only impact from price to sales is 0.015. So when the price goes up by 1, if this is an afternoon show, we expect an increase of sales by 0.015. On the other hand, if this is a morning show, then time M is 1 and the time E is 0. So we don't have the second variable, but we have the first one. And then the impact of price would be the sum of these two coefficients. And it gets to around 0.069. Okay, so that means this number is different from 0.015, and also the difference is significant. We expect the price sensitivity to be significantly higher in the morning than in the afternoon. Finally, the sales of evening may also be affected, but the impact is actually smaller than in the afternoon because the coefficient here is negative. Even though it is not significant, this information is useful, at least when we do some prediction. So, on the other hand, the average price also affects time's impact. Okay, so for the same table. We know that if we reschedule an afternoon show to the morning, or an afternoon show to the morning, in the past we say we expect a loss of 55 tickets, but that's not the whole story because we also have another term here, which measures the impact on the average price. So that means if we have a higher price, then we do not hurt that much when we reschedule to the morning. So for example, if the average price is 500, then we expect the sales to decrease by only this amount, only 28 instead of 55. If the average price is 1000, then we expect only a loss of about one ticket. Okay? Because the impact of time now depends on the value of the price. If we reschedule an afternoon show to the evening, as another example, then again, we know the expected impact would be this coefficient minus this one times average price. Okay, so following the same rule. It's not always the case that an interaction is significant. For example, if we suspect people's preference for time is affected by year, then we may want to add time E time M times year as our interaction variables. And if we really do that, we will see that all the variables that are related to time and year are insignificant. Okay? So that means people's preference over the show time do not really change from year to year. Or consider another direction, the trend from year to year. We say there is a decreasing trend, right? The trend from year to year is the same for a different show time. For the morning, we have a downward trend. For the afternoon, we have a downward trend. The slope may be somewhat different, but the difference is not significant. Okay, so in summary, we would say time and year, they don't affect each other. They don't affect each other, at least from our data set. So, though all the variables are insignificant, we typically do not remove them at the same time, right? Here, if we remove all of them, we lost the information from time and year. That's actually useful. So, you probably remember, if we only remove the last two variables, then time and year will go back to our model with a significant impact. So when you see some insignificant variables, do not try to remove them all at once. Try to remove them one by one. Okay? Because some variables may become significant after you remove some unimportant variables. Okay, summary. Two variables interaction may be modeled with a product term. If its coefficient is significantly non-zero, then we can say one variable's impact on the dependent variable depends on the other's value. There are already 3 rules for keeping variables. And this is a summary across sections. We did one thing called quadratic transformation. And if we want to keep the higher order term x2, then we must also keep x, so that the curve is complete. We have indicator variables. If we want to keep x k prime, where k prime is one of the indicator variables, then we must also keep all other xk. If we want to keep one indicator variable, we need to keep all. We have interaction. And if we want to keep xi, xj, then we must also keep xi and xj, even if xi and xj are not significant, even if x is not significant, because we need those coefficients even though they are not significant. But we need those coefficients so that when we make interpretations, that makes sense. That's the true thing we want to identify. So as an extended rule, if we have xi times xj k prime, where xj prime is the indicator variable and xi is something else. If we want to keep their interaction term, we need to keep all the related terms. We need to keep xi, we need to keep xjk for all the k. So that's something to keep in mind. Do not remove those individual variables if we have the interaction term. Finally, it's possible to add the product of 3 variables or even 4 variables into a regression model. That's possible. That's possible. But you need to have a reason to tell us that the impact of xi on the y variable depends on the product of xj and xk, something like that. If you have a story like that, you probably want to add this interaction term. But of course, it's a rare situation. Thank you.